Hi, I'm just going to run fairly quickly through some information about climate projections. I'm going to focus on what they do well and what they don't do so well. I'm going to start with some climate basics and then move on to how we make climate change projections and finish with looking at how useful climate projections are as indicators of the future. So firstly, some climate basics. Now, some terminology. Weather versus climate. You may know this already, but it's worth revisiting. Starting with weather, weather is something that we all understand. This is what we live and experience on a daily basis. It's been described as the current atmospheric conditions at a particular place and time. And we're looking at timescales of hours to days when we talk about weather. At slightly longer timescales, when we're talking about um, variations that happen between different months and seasons and years, or even decades, we're talking about climate variability. This is natural variation that occurs over those timescales. At the longer timescale again, we start to use the term climate. Here we're talking about weather data that's been collated continuously over several decades, usually 3 decades, and from that, you can then compute averages, and that's what we're talking about when we talk about climate. It's really the average state that we're talking about. And when we're talking about climate change, that's when we're talking about change that can be detected when you look at data over multiple decades and looking right out over sometimes multiple centuries. There's some key terminology that's really pertinent to understanding what we mean by climate change projections. Now we know the climate system is incredibly complex. This is an attempt to capture some of that complexity, and the arrows show you where there are meaningful interactions occurring between different components within the climate system. Basically, it's divided into 5 major components: the atmosphere, the hydrosphere, which is the water, and the cryosphere, which is where all of the ice sheets and so forth are, particularly around the poles, the lithosphere, which is just a fancy word for the land, and the biosphere, which relates to all of the living stuff like the forests and the crops and the humans and the other animals on the planet. So it is very complex, but we know that the atmosphere plays a major role in determining what's going on with the planet's climate. And solar energy, whilst it's not the only energy input to the system, it is far and away the major input. So those 2 parameters are key to understanding what's going on in the climate. Now, for some time, people had been interested in atmospheric composition, and as far back as the mid 1800s, people were researching what might happen if the composition of our atmosphere was to change. And Eunice Foote was one of the first, was a real pioneer in this area, where she did some elegant experiments where she just put some thermometers inside some glass containers that were sealed, that contained air, and then she pumped a bit of extra carbon dioxide into one of them and noted that that caused the temperature to increase within that canister when it was placed out in the sun. And she concluded that if we enriched the Earth's atmosphere with carbon dioxide, that the climate of the planet would increase in temperature. And others then picked up on that work. John Tyndall very famously extended that work, and then others since then have continued to explore the detail around that theory. So if we understand that the composition of something like something like carbon dioxide can make a difference to the climate of the planet, it's informative to then look at what's been going on with a gas like carbon dioxide in the atmosphere over a long period of time. And thanks to the fact that we can drill down into very thick layers of ice in places like Greenland and Antarctica, pull out cores of ice that contain very small bubbles of air that were trapped there when the snow first fell way back whenever it was, we can then analyze the contents of those air bubbles and work out the the concentrations of a range of different gases that were present in the atmosphere at the time that snow fell. And when we do this, we can go back. This plot shows data going back 800,000 years, and you can see that there's a cycle. It goes up and down, and it's ranging from somewhere around about 175 parts per million up to about 300. But it goes up and down, and that's a cycle that follows the ice age cycles. And then right at the end of this trace, in the last 100 years or so, the levels have gone up and then just skyrocketed. And if we zoom in, you can see this. If we look just at the last 2,000 years, you can see that it's tootling along here at around 270, 280, and then suddenly really ramps up. And that's the biggest rate of increase that's been recorded, and we're now sitting at the highest level of atmospheric concentrations of carbon dioxide that have been seen in 800,000 years. And in fact, there's strong agreement now that it's the highest it's been in the last million years. So that's interesting. We have some theory that says that increasing carbon dioxide in the atmosphere could make the planet warmer, and we've got some observations that show us that carbon dioxide has indeed been increasing in the atmosphere. What's the mechanism by which that might work? Most people have heard of the greenhouse effect, and quite often when people talk about it these days, it's in the context of climate change, and greenhouse effect is sort of seen as described as the cause of global warming. And that's true, but it's only partly true. The greenhouse effect is in fact a natural phenomenon that's always occurred, and if we didn't have the greenhouse effect, then we wouldn't be living on this planet at all, and there may not even be any life of any description on the planet if not for the greenhouse effect. But what we really should be talking about in the context of climate change is the enhanced greenhouse effect. So in a nutshell, the greenhouse effect is when the energy from the sun reaches the earth, it hits the earth and causes the earth to warm. The earth then radiates some of that heat back into space. Now, some of that radiated heat gets intercepted by gases that are in the atmosphere, the so-called greenhouse gases, and they cause the heat to be re-radiated back down to Earth. And just by getting the balance right between the amount that escapes to space and the amount that comes back to the planet, that's been perfect, and it's been able to maintain the Earth's temperature significantly higher than it would have otherwise been in the absence of the greenhouse effect, to the extent that life's been able to establish and sustain on the planet. That's great. What's happened though is, as we now know, increasing levels of greenhouse gas in the atmosphere have changed the nature of this balance. So less of the heat that's radiated from the Earth manages to escape out to space, because more of it is intercepted by the gas molecules, the molecules of greenhouse gas in the atmosphere, which in turn means that more heat is re-radiated back to the planet than should naturally be occurring. And that's leading to a ramping up of this greenhouse effect, so that the Earth's temperature increases, and the more greenhouse gases we have in the atmosphere, the greater that effect will be. So has this actually translated into temperatures that we can observe? It's great to talk about the theory, and it's good to understand why it might be the case, but is it actually the case? And when we look at the observations, yes, it absolutely is. This graph shows the average global temperature every year from about 1850 through to now. And what's global average temperature is not something that you and I can really relate to. What it is you take the weather observations from every weather station on the globe and combine that with other sources of weather data like satellites and measurements from ships and a whole bunch of different things, and then you turn that into a globally gridded representation of temperature, and then you can calculate the average across the whole planet. And depending how you do that, you'll end up with slightly different results. And this graph shows 4 different sets of data produced by 4 different research groups and shows the results from their so-called temperature reconstruction. And you can see that from back in the 1850s, there's only one of those reconstructions, and then sort of sometime after 1875, some of the others kick in. And you can see that there are differences in individual years. You know, here's a year where the Met Office's data says it's hotter than the NOAA data. But when you take a step back and look at the overall pattern, they're all telling the same story. There's minor differences, but really the story is very clear. The planet's temperature has been increasing, and that has really ramped up since the middle of the 20th century. So, enough about the science. How do we actually make the projections? Well, it's a bit more science, isn't it? Talked about how complex the climate system is, but most of us, when we look out the window, you know, we sort of see it like this. But it is complex, and luckily for us, we can turn that climate system into a whole bunch of different equations. And if you're a bit of a maths head, this is for you. This is really great stuff. For somebody like me, it's all just but anyway, that's okay. Luckily, there are very smart people who build these climate models. And what they do is, when you can turn if you can represent a process that's going on in the climate as a mathematical equation, you can use a computer to solve that mathematical equation. And if you've got a big enough computer, you can solve all the equations at the same time. And that's what we do with global climate models. This is kind of a graphical representation of how they work. The planet is divided up into a series of boxes, and those boxes are arranged in layers that are a sphere wrapped around the planet, or the virtual planet. And there's one at the surface, and then there's another one on top of that, and about 40 layers of boxes going up into the atmosphere, and about another 40 layers going down into the depths of the ocean. And the model, because it's a massive computer program, the computer program solves all of those mathematical equations in every single grid box simultaneously, taking data from the neighboring grid boxes as it does so, and then comes up with a result that describes the state of the climate at a point in time. And then it steps forward in time and does it all again, takes the data from the previous step into the next step, recomputes all of those equations, and has an understanding, a representation of the state of the climate at that point in time, and then steps forward in time again and again and again and again. And those time steps might be 15 minutes, 30 minutes, maybe longer, maybe less, but they basically step through like that in a sequence, and then you can run that through for decades or centuries or even millennia if you have the computational capacity. So that's fine. We can use the climate model to simulate the planet, the climate of the planet. But we know that the amount of carbon dioxide and other greenhouse gases in the atmosphere is crucially important to the state of the climate. That's fine, but we don't know what the future greenhouse gas concentrations are going to be. So like we do with any of these sorts of problems where we can't know, we set up some what if scenarios. And in the context of climate modeling, those what if scenarios are currently what's referred to as representative concentration pathways. Representative concentration because it's about the concentration of greenhouse gases in the atmosphere, and pathways because there are different ways of getting to the end point. And so we can look at what these representative concentrations look like in terms of emissions in gigatons of carbon, in this case, CO2 equivalent, for, say, a scenario where we continue to use fossil intensive energy sources, or a pathway where we rapidly decarbonize, and that's represented by this low one, and then some in between. And those emissions are translated into well-mixed concentrations of greenhouse gases in the atmosphere, and that's what this plot on the right represents. And you might hear people talk about these as RCPs, and then you might hear talk of RCP 8.5. That's this one, because that particular RCP, or representative concentration pathway, reaches a forcing, radiative forcing, of 8.5 watts per square meter at the end of the century. That's why it's called RCP 8.5, and the others are named in that same sort of way. And when we do this, we can produce simulations of the planet's climate that look very much like the real world. Here's a simulation from just one of the many climate models that are out there, and this one's producing very realistic looking weather patterns, the sorts of things that we're accustomed to seeing in the nightly news and so forth. So that looks good, but how useful are they as indicators of the future? Well, it turns out they're pretty good. If we use the climate models to simulate the climate of the 20th century, as is shown on the bulk of this plot, then we can see how the climate model how the climate model results for the 20th century compare to the actual observed results from all of the weather recordings. And this is for Australia, this particular plot, and the blue line that goes up and down shows the annual average temperature for Australia. The black line shows the running average through that up and down variability. But the pale blue band behind it shows the range of temperatures projected by a whole collection of global climate models, an internationally collaborative collection of climate models. And you can see that whilst, there's a few diversions, by and large, the climate models, when they've simulated the climate of the 20th century through to early 21st century, have lined up very well with what's actually been observed in Australia. But interestingly, if we change the way those models are set up so that they only use greenhouse gases that are the result of natural processes, and we exclude all the greenhouse gases that are the consequence of human activities, that climate is represented by this grey band down here. And you can see that the start of the run, it lines up, but by the time we get to the middle of the run here, it's already diverged. And by the middle of the 21st century, where the climate should be in the absence of human-induced greenhouse gases is a long way from where we actually are. And then we can look at, well, what do the models say about the future based on those representative concentration pathways? And that gives us a band of projected change in temperature. So that tells us that the models do a pretty good job of simulating the climate when we tell it what's going on with greenhouse gases. But what about how good the projections have been? We've done projections for about 30 years at CSIRO now, so that allows us to look back and look at, well, what sort of a job did we do with our projections back in 1992? And again, this is for Australia, and we're seeing the annual average temperature as recorded by the Bureau of Meteorology to this point, which is where our projections were released, and then in red, the Bureau's data going forward in time with the trend line from the 90s till now in this dashed red line. And the orange band, this cone-shaped band, shows the range of projected change in temperature from those 1992 climate change projections. And you can see that that lines up really well. Those projections did a great job of projecting what the future temperature for Australia might be. Now, those projections are a band, and that's the nature of climate change projections. But the up and down real world recordings fall by and large within that band. Sometimes they come a bit below, and you might also expect them occasionally to go a bit higher. But fundamentally, that lines up really well. That also gives us confidence that the projections are believable. So just really quickly to finish off, what can we do with this sort of information? There's a stack of things that we use climate change projections for. One of the really useful things, though, is to start to look at what does it mean in terms of the statistics around hot and cold extremes or extremes of rainfall. And here we've used some products that we've developed from climate change projections that develop daily temperature and rainfall data, and we've interrogated those to get at information about things like the annual average number of days greater than 40 degrees, the average annual number of days less than 2 degrees, and the average number of months in a year when rainfall is low, decile 1. So if we look at the 40-degree days greater than 40 degrees, in the data that we've used in this period in the past, we were seeing an average of 3.4. Now, if we look at the Bureau's Wagga Wagga weather station, they say 3.0, so it's fairly close. There's some methodological differences that account for that difference between the two numbers. But if we compare this 3.4 with what the projections say for the middle of the century under medium emissions, we've got 8 models that we've used to do this, and that gives us a range of between 6.1 and 9.6 days per year where the maximum temperature gets above 40. Under a high emission scenario, they're hotter, and that's to be expected. There's a greater number of days when we exceed 40 degrees, 8.4 to 14.4. That's a big increase. If we look at the number of nights when the minimum temperature drops below 2, in the historic data set, that's 34.2. The Bureau gives a slightly higher number, but the medium emissions numbers are from 20 to 26.5, and the high emission numbers lower again. We're seeing a reduction in the number of nights where it gets cold, 17 to 23.6. And in terms of the rainfall, you can see the average from the 1981 to 2010 period is 1 month per year that falls within decile 1. By mid-century, we're seeing that increase by somewhere between 1 and 1.8, depending on emissions and depending on which model. But remember, these numbers are all long-term averages, so they sometimes they'll be more than that, sometimes they'll be less. So that's all interesting stuff. I'm going to have to finish there, but I just wanted to reiterate one final point, and that is that climate projections, the results will depend on our emissions pathway into the future, as represented by the coloured bands on this plot, but also the way in which the climate evolves over time from year to year will vary. There's no way we can predict exactly what that will be. There will always be a range, and I'm showing you this plot because each of these lines is the simulation produced by one of the many climate models that we use, and you can see that there's a difference even within a given emission scenario. You get a different sequence of years depending on which model run you look at, and that's just a fact of life. We can't predict exactly how this is going to play out, so we talk instead about just the mean state of the climate, the range of change, and what's plausible looking forward into the future. So to wrap up, climate models do a pretty good job of projecting plausible future climate states, but they're projections, not forecasts. We can't tell you what the annual average temperature is going to be in 2065. We can't tell you if the 2070s are going to be dominated by El Nino or La Nina, but we can talk about the mean state of the climate. And a range of future climates are always possible, and that will always be so. There's a element of chaos in the climate system that means that it's impossible to ever predict exactly what the future climate will be, but we can set bounds around it, and that is enough to inform really sensible decision making going forward. Thank you very much.